thing is, EM waves are quite weak. Even if the antenna transmitter is transmitting at high power, at a long distance away, you're gonna lose a lot of the signal. So the power is proportional to the distance squared. So if you're 4 times the distance away, that's 16 times less power. So it's quite dramatic. So if we have the antenna here in our circuit, this signal will need to be amplified. And so we can round that through a transistor circuit. So let me see if I can explain this. So we have the signal. It'll come in here as a wave. It'll charge this up. So it'll draw and sink current into this capacitor here. So basically, if we do a Kirchhoff's junction rule here, we're going to have an amount of current going down here, but we're also going to have an amount of current going through here. And what's going to change is this one here. This will sink or draw. So either when the signal, because it's an alternating signal, so when it's positive or negative here, it's going to draw current. So current's going to charge up here, and on the other wave, it's going to draw current out of it. And so what it's going to do is it's going to change the amount of current that goes through here, down here. So we have this large voltage source here. It's being choked by the inductor. So the current is going to, first of all, this circuit is going to charge up this capacitor here to full, or whatever the voltage is here. It's going to be across here. But then when the signal comes, we're going to be sinking current out of this capacitor down through this BJT transistor here, right? So depending on our signal, we're going to be sinking different amounts of currents here. And because the current is choked here, it's going to have to draw that current from the capacitor. So we're going to get a lot of fluctuations here. So if we do a Kirchhoff's loop rule, we'll begin here and go through this way to ground. So we'll have the plus voltage source. We're hitting it from the negative side. So let me redraw this loop to make it a little bit more explicit. Here, this capacitor is this capacitor here. Okay, and we have to redo that. Plus VC is equal to 0. Okay, much better. So now we can solve for VL, which is what we're looking for. So let's throw everything over to the other side, except for VL. So we have VL is equal to the voltage source V minus VL minus VC. And because the voltage drop across the inductor is negligible, let's just remove that. So what we get is that the output signal is now this large voltage minus whatever the capacitor voltage is here. And remember, this voltage is going to fluctuate based on what we sink here. Remember, if we put more current in here, we're going to have a higher voltage. If we take current out of it, we're going to have lower voltage. So this will fluctuate the same way as this signal does here. So we have a copy of our receiving signal that was transmitted on here, thanks to the choke here. And so that looks like the same wave. So let's say this is the wave we sent out. On here, let's say we connect the speaker here. We're going to have that exact wave just shifted up, biased up by V. Hopefully that makes sense. And this is enough voltage to drive a speaker. And depending on your transistor, the current going through here will be 10 to maybe 100 times smaller than the current that goes through here. So there's a way to mathematically explain that. So the current at the base is proportional to some kind of constant, maybe 10 times whatever the current is through the emitter. So whatever current, so yes, this current here that we get from the signal will be mirrored here and sunk out of the capacitor here, but at a greater value. So you'll have larger swings and fluctuations here. So depending on your transistor, you might not get an exact copy here. That would mean this would be 1. You might actually get 10 times or 100 times the amplification on your signal. And if you remove the DC bias here, you will get this voltage form like this. And it would have been amplified by perhaps 10 times or more, depending on your transistor. Hopefully radio starts to make a little bit more sense now.